We're going to go through practice drawing the Lewis dot structures of many different molecules and ions, and you'll see that we go through the same general procedure each time. The procedure is best illustrated as we work through some examples. The first step is to count up all the valence electrons. In this, we add up the group number of all of the atoms and we account for any net charge. So here's how we have done that for acetylene. We see hydrogen, there's 2 hydrogen atoms. It's in group 1, which means there's 1 valence electron per hydrogen atom. Carbon, 1 of those, group 4. Oxygen, 1 of those, group 6. So we have a total of 12 valence electrons. When I do Lewis dot structures, I work in terms of electron pairs. Things go much faster, the diagrams are much cleaner. 12 total valence electrons would correspond to 6 electron pairs. We're on to the second step, where we arrange the atoms around the central atom and complete the octet of the outside atoms. In Chem 110, you're going to be given the skeletal structure. So we have already arranged the atoms around the central atom, but we're going to connect them up using the electron pairs that are available to us. So we use our first 3 electron pairs to connect up these atoms. Next, we want to complete the octet of the outside atoms. We'll remind ourselves of the octet rule, is that atoms tend to ionize or combine to achieve 8 valence electrons, and also remind ourselves that hydrogen and helium follow the octet rule, but they only need 2 electrons to complete their, quote, octet, unquote. A bond is a pair of shared electrons, and a key result of a bond forming is that these bonding electrons count towards the octet of both of the atoms that are involved in the bond. So thus we see hydrogen, both of these hydrogen atoms now has a complete octet. First of all, they only need 2 electrons for their octet, and when we consider that these bonding electrons count towards the octet of both hydrogen and carbon, each of these hydrogens has a complete octet. Let's look to the other outside atom, oxygen. Thus far, oxygen only has 2 valence electrons. However, we've only used 3 of our 6 electron pairs. So we can put the remaining electron pairs around oxygen, and we see now oxygen has a complete octet, i.e. it has 4 electron pairs, 1, 2, 3, 4. Each pair, each line represents 2 electrons. So oxygen has a complete octet. Oxygen has 1 bonding pair and 3 non-bonding pairs assigned to it. These pairs of electrons that are not involved in bonding are called lone pairs. Now we'll look to our central atom, carbon. We want to complete the octet of the central atom. However, we've used up all of our electrons. All of our valence electrons are used up. We have 6 electron pairs. They're all currently being used. However, carbon is electron deficient. So if we look at the carbon atom, it has only 3 pairs of bonding electrons assigned to it currently. Therefore, it has 2, 4, 6 out of the 8 valence electrons it needs. And that's why it is called electron deficient. We're going to go to the next slide to see how this is going to be handled. So this is where we finished on the previous slide. We have carbon bonded to the 2 hydrogens and oxygens. However, the central carbon atom is electron deficient, and we've used up all of our 6 electron pairs. We're going to use one of the lone pairs and convert it to a bonding pair. As before, each of the outside atoms has a complete octet. Each hydrogen has 2, and the oxygen has 8. 2, 4, 6, 8. However, we see now the effect of converting this one lone pair to a bonding pair, is that now carbon has 2, 4, 6, 8 valence electrons assigned to it. It has a complete octet. Now we're done with this problem, but I want to make a few points before we go on because they'll be important to the rest of your chemistry career. A single bond is going to be represented by 1 electron pair, a double bond by 2 electron pairs, triple bond involves 3 electron pairs, and they can be represented this way. In terms of bond strengths, a single bond is weaker than a double is weaker than a triple bond. There are multiple ways to represent an electron pair. I tend to use a single line. Occasionally you'll see either 2 X's or 2 dots. They all represent an electron pair. We're going to do many more examples of drawing loose dot structures, but I want you to notice that they're all going to follow the same basic procedure. Count up the valence electrons, arrange the atoms around the central atom, complete the octet of the outside atoms, then look to the central atom, and in completing the octet of the central atom, you may have to use double or triple bonds. In prep chem, you're not going to encounter this last step, but you will in general chemistry. If at the end of these first 3 steps you have extra electrons, you can just take those extra electrons and dump them on the central atom. When we count up valence electrons in sulfur trioxide, we see we have 24 valence electrons, 12 electron pairs. We connect up the atoms, and now we complete the octet of the outside atoms. So far we've used 3 of our 12 electron pairs. So that's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. When we look at our outside atoms, we see each of the outside atoms has 8 valence electrons. Again, remember the bonding electrons count towards the octet of both the oxygen and the sulfur, both atoms in the bonding pair. The sulfur atom right now is electron deficient. It needs 1 more electron pair, so we need to make 1 double bond. So we are representing this 1 lone pair being converted to a bonding pair. The resulting structure is this one down here. The question you may have is, well, how do I know if I need a double bond between sulfur and this oxygen atom, or this one, or this one? And the answer is, it doesn't matter. These are all equivalent structures. When you move on to Gen Chem, you'll learn that these are called resonance structures. For now, know that any one of these 3 is an appropriate answer. Boron trifluoride. 1 boron, it's in group 3, 3 valence electrons from boron. 3 fluorines, each in group 7, so they each contribute 7. We have a total of 24 valence electrons, or 12 E pairs. When we connect these up, we see we've used 3 of our 12 electron pairs. The remaining pairs will be used to complete the octet of the outside fluorine atoms. Boron trifluoride represents a special case. Neither boron nor fluorine atoms will form double or triple bonds. The result is that boron in this compound is left electron deficient. And you will learn in resulting chemistry courses that because boron is left electron deficient, boron trifluoride is a very reactive compound and will react with many other chemicals very readily in an attempt to complete its octet. Ammonia, NH3, 8 valence electrons, therefore 4 electron pairs. Once we connect up our outside atoms to the central atom, we see we've used 3 of our 4 electron pair. The remaining electron pair goes on nitrogen. And we can see how all of the atoms have complete octet. Again, remember the bonding electrons count towards the octet of each atom in the bond. So hydrogen has 2, 2, 2. Each of the 3 hydrogen atoms has a complete octet of 2 electrons. Remember, hydrogen, helium, they only need 2 electrons for a complete octet. Nitrogen has 1 lone pair, 3 bonding pairs, but all of these pairs count towards its octet. It has a complete octet of 8 electrons. When we count up the valence electron on the phosphate ion, we need to account for the fact there's a net -3 charge. The net -3 charge indicates that there's 3 extra electrons that we need to add to the total. So when we're totaling our valence electron, we have 1 phosphorus atom. It will contribute 5 valence electrons. 4 oxygen atoms. Oxygen's in group 6, so each oxygen is going to contribute 6 valence electrons, a total of 24. And we add on the extra 3 E's that are there from the net 3 charge. So we have a total of 32 valence electrons, 16 electron pair. Connecting up the outside atom consumes 4 of our 16 electron pair, and the remaining electron pairs go on the outside oxygen atoms, and we see we have a total of 16 electron pairs. When we represent this ion, we want to show that this whole ion has a -3 charge associated with it. Sulfite ion, SO3 2-. 1 sulfur atom, 6 valence electrons, that's in group 6, so we get 6 from the sulfur. Oxygen's also in group 6, we have 3 of those, so 18 valence electrons from the oxygen. The -2 charge indicates we have an extra 2 electrons, so we add this up, 26 electrons, 13 electron pairs. We use 3 electron pairs to connect up our outside atoms. Now we need to complete the octet of the outside atoms. So that's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and we have 1 more pair of electrons to complete the octet on the sulfur. Reminding ourselves that bonding electrons count towards the octet of both of the atoms in the bond. We have a complete octet on all atoms. Each of the oxygens has 4 electron pairs, or 8 electrons. The sulfur has 3 bonding pairs, 1 lone pair, for a total of 8 valence electrons. The perchlorate ion has a total of 32 valence electrons, 16 electron pairs. We can connect up our outside atoms and complete their octet, and we see that consumes all 16 of our electron pairs, but all of our atoms have a complete octet. We can see the octet rule followed. Oxygen atom 2, 4, 6, 8. On each one of these oxygen atoms, the chlorine atom has 2, 4, 6, 8, and we indicate that the whole thing has a -1 charge. Our nitrite ion, NO2-. Nitrogen gives us 5, the 2 oxygens give us 12. We have an extra electron. We can see, as is indicated by the negative charge, 18 valence electrons, 90 pairs. We connect our atoms and complete the octet of the outside atoms. We see that we have 1 electron pair to give us to nitrogen, but nitrogen's electron deficient. We can see that nitrogen's electron deficient because we have 2 bonding pairs and 1 lone pair for a total of 6 electrons. So we need to use one of these lone pairs to make a double bond or one of these lone pairs to make a double bond. It doesn't matter, they're both equivalent. So we can write 2 correct Lewis dot structures for the nitrite ion. Either one would be acceptable. When we go on to Chem 115 and Gen Chem, we'll see that these are what's called resonance structures.